Download this code from codegive.com, link in the description below. Blocking system calls, Stack Overflow, and C, a deep dive. This tutorial explores blocking system calls in C, a common source of issues, particularly when coupled with potential Stack Overflow problems. We'll examine the concepts, their interaction, and how to mitigate related risks. 1. Blocking system calls ***. Many system calls in C, functions that interact directly with the operating system kernel, are blocking. This means that when a blocking system call is invoked, the calling process is suspended until the system call completes. The process is essentially put to sleep, relinquishing control of the CPU. It won't continue execution until the operating system signals that the requested operation has finished or an error has occurred. Common examples of blocking system calls include *read, reads data from a file or socket. If no data is immediately available, the process blocks until data arrives or an error occurs. *write, writes data to a file or socket. If the buffer is full or there's a problem with the write operation, the process blocks. *req, receives data from a socket, network programming. Blocks until data is received or an error happens. *accept, accepts a new connection on a listening socket. Blocks until a client connects. *connect, establishes a connection to a remote host. Blocks until the connection is established or fails. 2. Stack Overflow ***. Stack Overflow occurs when a program attempts to use more stack space than has been allocated to it. The stack is a region of memory used for storing local variables, function call parameters, return addresses, and other temporary data during program execution. Each function call adds a new stack frame. Recursive functions or very deep function call chains can easily exhaust stack space. This leads to program crashes, segmentation faults, or unpredictable behavior. 3. The interaction, blocking calls and Stack Overflow. The danger arises when a blocking system call is made within a deeply recursive function or a function with a large number of local variables. If the system call blocks for a prolonged period, the stack remains occupied. Further recursive calls or function calls within the block section can lead to Stack Overflow before the blocking call completes. The process is essentially stuck in a state where it cannot proceed and has no space to handle further function calls. 4. Code example and explanation ***. Let's illustrate the problem with a simplified example of a recursive function making a blocking read call. This example simulates a scenario where data might not arrive immediately, example a slow network connection. Explanation ***. ***read, recursively calls itself. Each call adds a new stack frame, containing buffer, bytes_read, depth, etc. ***if read, blocks, example waiting for data from a slow source, the stack remains in use. The recursive calls continue to add stack frames, eventually leading to a stack overflow if the blocking lasts long enough and the recursion is deep enough. The buffer size is relatively large to exacerbate the stack consumption problem, demonstrating the impact of local variables. 5. Mitigation strategies To prevent this scenario. Avoid deep recursion if possible, refactor your code to use iterative approaches instead of recursion. Increase stack size, use with caution. You can try increasing the stack size limit at compile time, example using ulimit s unlimited on Linux or compiler-specific options. However, this is generally not a robust solution and can mask underlying problems. Very large stack sizes can still lead to failure or can consume significant system resources. Non-blocking IO * use non-blocking system calls, O_non-block flag with open, or similar functions for sockets. With non-blocking IO, read, would return immediately, either with data or an indication that no data is available. This allows your program to handle other tasks or check for errors without getting stuck. You'll need to implement appropriate error handling and polling or select mechanisms to manage non-blocking IO effectively. Asynchronous IO for more advanced scenarios, asynchronous IO, example using AIO functions or libraries like libvent or libov, provides a more sophisticated approach to handle IO operations concurrently without blocking the main thread. This is particularly beneficial for high-performance or high-concurrency applications. Threads consider using threads. If a blocking operation is needed, perform it in a separate thread. The main thread can continue execution without being blocked, minimizing the risk of stack overflow. Proper synchronization mechanisms, mutexes, condition variables, are essential when using threads. Example with non-blocking IO, illustrative. This example is simplified and requires adaptation depending on the specific situation. It demonstrates the basic concept of preventing blocking by checking for data availability before reading. This non-blocking example is much safer than the recursive blocking example. It manages the lack of immediate data without causing a stack overflow. By understanding the nature of blocking system calls and the potential for stack overflow, and by employing the appropriate mitigation strategies, you can write more robust and reliable C programs. Remember that the best approach depends heavily on the specific application and its requirements. Choosing the right solution necessitates careful consideration of factors like performance, complexity, and maintainability.